So, good morning, everybody, to the second edition of the International Seminary or graduate course in the Instituto Tecnológico of Celaya. Today we have the participation of the Professor Alex Dowling. So he is professor at the Chemical Engineering Department at the University of Notre Dame. He has a very interesting group in process system engineering, and today he is gonna share with us some of the topics about uh, scalable systems and uh, some works in optimization and control. And okay, Alex, is your audience. So, okay, thanks for accepting our invitation to this uh, to share with us your work.
Great, and thank you so much for the invitation and the opportunity to present. Um, so as Luis Fabian mentioned, I'm going to be talking about kind of how process systems engineering, modeling, and optimization control, how those ideas can be applied to the electric grid and energy infrastructure. Um, Before I jump into that, I just want to tell you a little bit about the University of Notre Dame. So we're a private Catholic university that's in northern Indiana. Many argue that this is the most beautiful campus in the United States. So I have some pictures from around campus, the Golden Dome, the Statue of Mary on top. That's the main administration building, the library with the Mirror of Life image, the grotto, and the American football stadium. There's about 9,000 undergraduates and 4,000 graduate students at the university. And we're split into the College of Arts and Letters, the College of Science, the College of Business, and the College of Engineering. Inside the College of Engineering is Chemical and Biomolecular Engineering, which is my home. We're one of 5 departments. We're nominally broken into 3 research areas: human health and well-being, energy and sustainability, and data science and modeling. Many people like myself work across all of these areas, but in total, there's 23 tenure track faculty, 4 research faculty, 3 teaching faculty, for a total of 240 undergraduate students and about 100 graduate students. So kind of within this context and inside the department, I am the expert in optimization and statistics and modeling. So what my group focuses on is what we call molecular to systems engineering. So this idea of, as chemical engineers, we like to think about maybe energy problems and think about them across molecular to infrastructure scales. So thinking about designing new molecules that enable new materials, that enable new devices, that get integrated into systems that then have impact at infrastructure scale. Another way to think about this is this diagram on the right. And there's a lot of complexity in connecting the device to the system scale. And this complexity is intentional. And what my group does is uses modeling and optimization to really cut through this complexity. So compared to my colleagues at Notre Dame, a distinguishing aspect of my group is we formulate everything as a mathematical optimization problem. So we think about writing objectives and constraints subject to either continuous or discrete variables. And we apply these to a lot of problems and collaborate with about 10 different research groups on campus. So everything from novel separations to carbon capture to additive manufacturing to desalination to systems biology, and finally to energy markets and energy infrastructure that I'll talk about today. Cutting across all these applications are 3 main pillars or 3 main ideas that our group works on. The first is molecular systems modeling. So how can we use models to set material property targets? So here's an example of thinking about membranes for removing lead or other contaminants from water, and understanding how much membrane material you would need is a function of 2 material properties. And this can help guide our experimental collaborators. And the other second pillar is optimizing experiments. So here we work with our experimental collaborators to think about how to build mathematical models and then apply data science tools like model-based design of experiments to think about really what's the minimum set of data that we need. And then finally, what I'll really be focusing on today is scale bridging models. So when I showed that molecular to infrastructure, how do we connect those models across scale and how do we deal with complexity? And a lot of this is using machine learning ideas. So shown here is looking at some reaction kinetics where we have a hybrid model that contains both a simple component and a machine learning component to take care of the error in that. So I'm going to be talking about energy markets and this last column, scale bridging models, and I'll bring that out throughout the talk. In 1 second, I'm just going to check a microphone setting. Oh,
it is fine. Everything is fine.
Okay, I was hearing a little bit of an echo on my end. Okay, so now to get into the main talk. So as you probably all know, we have this really big energy transition ahead of us. There's a lot of interest in sustainability. So here's a map of the United States. Every colored box shows a different state in some of their renewable energy targets. But integrating more renewable energy is not without its challenges. So shown here is the so-called duck curve. So what this is the average power demand is a function of time. So from midnight to noon to midnight for a day in California. And each line corresponds to a different year. So we see here, starting with 2012, the average electricity demand. And as each year progresses, this plot becomes more and more extreme. There becomes less and less net electricity demand in the middle of the day, and there becomes more and more of these extensive ramping events. And this is because of solar energy, which is producing a lot in the day, but then you have these ramping events due to the sun setting. So this is one challenge, this daily variability. Other challenges are seasonal and caused by unplanned events. So what's shown here is generation, so electric power demand in megawatt hours shown during a blizzard event in the United States over a couple of months. And what we can see here is the fluctuation in different modes of power production. So a question is, how do you deal with this variability, this daily variability and this seasonal and up to annual variability? And one leading idea is to design integrated energy systems that hybridize multiple technologies. So thinking about multiple energy inputs, whether it be nuclear, gas, fossil fuels, solar, wind, batteries, into this integrated system that can produce multiple products like electrical energy, hydrogen, chemicals, heating or cooling, and is integrated in a way that synergizes these different technologies and it exploits their coupling to provide more flexibility to the grid. So a key question here is, how do you design these systems? How do you operate these systems? And how do you control these systems? And for the rest of the talk, I'm going to discuss how we use mathematical optimization to do that. Before I kind of get into this, I want to give a background on energy markets in the United States. So energy markets in the United States are just really fascinating, kind of broken up into about 10 different regions or 10 different markets. I'm going to focus on California just as an example. Every dot in this plot is a node in the California electric grid. There's about 8,000 nodes. And you can zoom in at every node, and there are electricity prices set on 3 time scales. There's a day-ahead market that sets prices in every hour. There's a 15-minute market, and then there's a 5-minute market. These are referred to the day-ahead and the real-time market. What these are histograms showing over the course of an entire year from 1 to 3 p.m. prices. And what we can see is approximately normally distributed in the day-ahead market. But as we go to these faster time scales, we get more and more extreme prices, and this starts to become bimodal. Shown here is a time series over about a week. And what we see are a lot of evening price spikes, which are due to that duck curve I previously discussed. And we see a lot more volatility in the faster timescales. If you're curious, we've even done some Fourier analysis and looked at what the dominant modes are, and I'll refer you to these papers. So what we have in this figure is these three time scales, but now looking at them across one snapshot in California. So these are simultaneous prices, and we even see a lot of spatial temporal variability. So if you want to think about energy systems in California and prices, in 1 year, you have about 1 trillion prices. And if you just were to represent this as text files, uncompressed, it'd be about 500 gigabytes. There's a lot of localized variation at slower time scales, and there's system-wide variation at really fast time scales. So if you're a resource, so if you're a power plant, or if you're an industrial producer or a large residential complex, you have to think about how do you interact in these markets. And there's several ways to interact in these markets. So I want to explain this figure. Sorry, there's a lot of text here. Starting at the slowest time scale, you can transact energy in the day-ahead market, followed by the 15-minute market or the real-time dispatch market. So that's for transacting electrical energy. Alternately, you can transact ancillary services. And these are ways of communicating flexibility to the grid. So spinning reserves and non-spinning reserves are saying that you're going to be in a standby mode and ready to produce power if called upon. Or power regulation, where you're actually tracking the signal from the grid on an order of seconds. And what you see across all of these different market products is as we go from slower to faster time scales, the amount of money that we can get in the revenue opportunity goes from small dollars to a lot. There's really rich literature in the process systems engineering community about how to transact and how to interact in these markets from a resource perspective. There's a lot of scheduling literature thinking about time-varying prices. There's optimization literature thinking about reserves and interruptible loads, frequency regulation, and chemical engineering systems. So in the context of this really rich literature, I want to talk about how to make these market participation decisions and co-optimize how we participate in the market and how we design and operate integrated energy systems. And to do this, I want to introduce some ideas that we've come up with as part of this IDEAS, Institute for Design of Advanced Energy Systems, and dispatches. These are two U.S. Department of Energy funded large collaborative projects. So for the first half of the talk, I'm going to discuss a price taker assumption to optimizing these integrated energy systems. In the second half of the talk, I'm going to discuss going beyond price taker. So my goal is at the end of this talk for everyone to kind of understand various aspects of this figure. So let me start with price taker, which is the simplest. And here what we have are either historical price data or price data that we get from running a production cost model. So this is like a model for that mimics how the grid schedules resources. Those provide locational and marginal prices. We can maybe do some data analysis like clustering or thinking about forecasting, but we have price data as inputs to an optimization model. And what this looks like is an optimization formulation like here. So here we're moving beyond levelized cost electricity, and we're going to co-optimize design and operation of an integrated energy system. So our objective would be to maximize the sum of the revenue. So that's the price, which is a market input, times the amount of power we produce, minus the costs. And those costs include variable costs and capital costs. So what goes into the optimization problem is a market price. What comes out is a power production schedule as a function of time, and optionally a nameplate capacity or a sizing of the system. This can be constrained by ramping rates, and many systems actually operate in modes. So perhaps there's a different model for a plant being off versus a plant being on. So we're going to take this idea of a price taker assumption where we take input data and we fix and we assume it doesn't change, and we're going to use this to analyze a variety of integrated energy systems. So the first example I want to talk about is the question of, should we build a battery in California? So California has mandates within the next year and a half to install over 1 gigawatt of battery energy storage in the state. And here are actually three installations that went in about 5 years ago. And you can see that these are all rated to have 4 hours of energy storage. They're all very large, and they're all lithium-ion battery technologies. These three installations are shown here. So in light of these installations, we wanted to ask the question of, if I take historical price data from California, what is the revenue potential for these batteries that are being installed? If these batteries were to participate in the market, how much money could they make? So here we can formulate a variation of this price taker optimization problem, where we want to maximize our market revenue, assuming perfect information, constrained by bidding rules, constrained by the market dynamics. So we're going to assume price taker, and constrained by the physics of the battery system. So we're going to be able to interact in these three markets. We can purchase electricity, we can sell electricity, and we can provide ancillary services. And we're going to characterize our battery with some type of round trip efficiency. We're going to fix the power rating to 1 megawatt, and we're going to optimize the storage size. So our decision variables are going to be, how do you participate in the market? And the input data is going to be the prices. So we ran this analysis for a bunch of different storage sizes in hours. And we got this really interesting plot. There's a lot going on here, so let me explain it slowly. This line right here corresponds to if I had a battery and I could only buy and sell energy in the day-ahead market. And what I want to draw your attention to is this left axis is the payback period in years. So what we can see is, even as we vary the energy storage size, it takes at least 60 years to pay off the capital on the battery. It doesn't make sense from an economic perspective, based only on transacting energy. If I then add ancillary services, and at top of energy, I move down to this blue line. And then if I add energy and ancillary services in both the day ahead and the real-time market, I get down to this green line. So what this is telling us is it's really important, if you think about a privately owned battery, that it transacts in both markets, and actually the markets incentivize a smaller battery that has a lot of flexibility and can provide these frequency regulation services. So this is analysis for one node in California, one set of price data. We then repeated this for all the nodes in California that we had a data for, and we're focusing on full market participation. And what we found here is there's actually some variability in the market payoff, and it goes from a 1-year payoff period to almost a 2-year payoff period. And what we found was really interesting, that the best payoff period based on the historical market prices is actually in the middle of the state. We were expecting it would be closer to the coast, where there's more variability and volatility due to the large cities. So this opens an interesting question of, the market's incentivizing storage in the middle of the state. Is that actually where the grid needs the storage? And if not, maybe there's some interesting market design opportunities. So this is like a nice first analysis, and what we learned from this is the importance of transacting both energy and ancillary services. And we thought about a battery, but one of the key aspects of a battery is degradation. So then in the next part of this study, we changed technologies to a sodium sulfur battery, and we extend our optimization formulation to think about degradation. So we added to the optimization model this degradation counter, that as we charge and discharge the battery, we slowly change the upper bound on amount of energy that could be stored in the battery. So we're very clever about how to write this, so it becomes a linear program. We can then write or formulate the program over multiple years. So with 5 years, you have about 4 million variables, about 6 million constraints. But because it's a linear program, you can solve it with Gurobi or other commercial optimization solvers in about 2 CPU hours. So that's actually really nice. So what we did is we then took this model and we resolved it for a bunch of different market participation modes. So what we see on this plot on the left is looking at the economics. Each of these kind of clusters is thinking about, am I transacting day-ahead energy, real-time energy, or in both markets? kind of within each cluster, there's two groups. The first group is energy only. The second group is energy and ancillary services. So what we're showing on this plot is net present value. This plot is organized the same way it's showing battery capacity. So what do we find? Well, consistent with our previous results, we find that it's really important to provide those ancillary services. They provide a huge bump in net present value, and they facilitate a really big bump in energy storage. What was a lot more surprising to me was we considered different degradation scenarios. So the gray line was super optimistic, no degradation, where you could cycle the battery an infinite number of times before it failed. The red line was an order of magnitude better degradation than current state of the art. Blue line was kind of current state of the art, and green line was an order of magnitude worse than current state of the art. And what was really interesting is we see these order of magnitude changes in degradation don't have that much of an impact on the economics. And the reason for this is there's so many degrees of freedom in how you can participate in the market. So what this means is if you have a battery that's today's battery that has some degradation concerns, there's so much flexibility in how you participate in the market. You could decide to adjust your schedule for buying and selling energy or arbitraging energy to avoid too much cycling and to manage that degradation. We then took this a step further and resolved the optimization problem with a bunch of different replacement strategies. So do we replace the battery every 3 years, every 4 years, all the way up to every 20 years? And then what we plotted was the revenue that we would get for no degradation and those 3 other degradation scenarios. You can also compute a very optimistic upper bound where we would expect these lines to converge for no degradation at a time scale at a replacement lifetime of infinity. So this kind of corroborates the results on the previous slide that shows that you can still manage degradation over really long time scales by adjusting how you participate in the market. So kind of the conclusion of this part 1A of the talk is it's really important when thinking about energy systems that have storage that are participating in a market to be thinking about multiple market products, because arbitraging energy on the day-ahead market is really not that profitable. You need to be transacting ancillary services. So we've done a bunch of work looking at batteries, and we've also done some work looking at concentrated solar power plants for this. Now, maybe a limitation of this work so far is we assumed perfect information. We were computing operating profiles, assuming that there was no uncertainty in the market price and you could forecast the future. So that raises a natural question about what about uncertainty? So we've done a little bit of work in the group. One was to propose these autoregressive Gaussian process models to forecast uncertainty. These provide nice confidence bands. And in another work that I like to talk about today is dynamic mode decomposition. So I'm a member of the Society of Industrial and Applied Mathematics. And at least before COVID, when you'd go to their conferences, they'd have a book sale. And I'm always a sucker for the book sale. I almost always buy some books. So when I went to SIAM at UQ in 2018, I bought this book, Dynamic Mode Decomposition. I heard a lot about it. It had a really nice cover, and I got curious. Shortly after coming back from that conference, I had a really bright undergraduate student, Clay Elmore, ask me about research. I gave him the book and said, I had this interesting data set. Let's see what we can find from this. So what we're going to do is take this spatial temporal energy market price signals, and we're going to ask, can we come up with a really fast way to forecast future price signals using dynamic mode decomposition? The main idea behind dynamic mode decomposition is we want to find the best small or low rank linear system that approximates a dynamic system. So what I mean by dynamic system is you can think of each price, the price at each node here is a state variable. So maybe I have 8,000 state variables. And I want to know kind of the dynamics of how prices evolve for each of those state variables. So the way that this works is you have all of your time series or your spatial temporal data that you can put in the matrix X and X prime. They're just time shifted by 1. And you want to find the best linear system A that when you operate on X advances and gives you X prime. The way that you can do this is you can take X and perform singular value decomposition. You can then truncate that singular value decomposition, and that will give you a space that you can project, and then you can get this approximate low rank operator A. What's really nice is because this is a linear system, the DMD modes correspond to the eigenvalues and eigenvectors of this matrix A. So what you get at the end of the day is this really nice analytic formula that approximates the dynamics of your system. So we went to apply this to our energy market data, and we found a problem. So in dynamic node decomposition, there's this well-known problem called the standing wave problem. So if you consider this really simple system, X is a function of sine of t, you'll actually find the system you can't reconstruct with plain dynamic mode decomposition. And the reason is that this system is actually the solution. This system is actually the solution to a second order differential equation, and dynamic mode decomposition doesn't. It's just a first order method. So to overcome this, what's really common is what's known as augmented DMD, where you just stack or augment the data. And this is just like differencing in time series analysis, where you difference your model to get up to these higher order. So kind of armed with this augmented DMD, which overcomes this nuance, which is really important because we're analyzing cyclic data, we're then able to test dynamic mode decomposition. And we did a really nice study where we were comparing standard versus augmented DMD. We found that augmented DMD does indeed find a low rank structure. It can do much better reconstruction error. So it can reconstruct the data. It fits the data better. And it does a reasonable job at forecasting. So shown here in green is our training data. In red is our testing data. Our DMD forecast in blue doesn't make sense. Our augmented DMD forecast actually looks really nice. Great. So we have a way of forecasting energy prices, and it's actually a lot faster than some traditional time series approaches. How does it help? So then we set up a case study where we asked our question, how much does uncertainty impact the market revenues? So we set up an optimization problem just like we saw before. And the only thing that's different is instead of these prices being perfect information, we used forecasts. And we compared DMD, augmented DMD, and then backcasting, which is a really simple approach where you just take the previous day's data and that becomes your forecast. And what was really surprising to us is, augmented DMD worked really well. Despite the fact that it's not perfect, you can capture 81 to 92% of the revenue. So that was really nice to see. The thing that surprised us even more was that backcasting, this really simple approach where you just take the previous day's data and that's your forecast, worked almost just as well. And what this told me was, for these market systems, uncertainty might not be that big of a problem, which was not what I expected when we started this project. All right. So we've spoken about uncertainty. We've spoken about perfect information and batteries, but what about other technologies? So now I'm going to transition to talking about other technologies and integrated energy systems that can co-produce power and hydrogen. So there's this growing popularity of the idea of the hydrogen economy, where we're going to have hydrogen as an energy carrier that can be used for the transportation sector, that can be used in refineries. And we need to think about how do you make hydrogen in an environmentally responsible way. So one way is through these integrated energy systems that leverage things like fuel cells that can convert natural gas directly into electrical energy and hydrogen, as well as electrolyzers that is kind of like a fuel cell operated in reverse that you can use to take electricity and create hydrogen that can then be stored and sent to hydrogen users. So the question is, can we come up with integrated systems that co-produce this electricity and co-produce this hydrogen together? And are those systems more beneficial than having separate infrastructure to generate electricity and hydrogen? So this is in collaboration with the National Energy Technology Laboratory as part of this IDEAS project. And what we did in this project is we came up with 6 different concepts for power production or hydrogen production. Natural gas with carbon capture, solid oxide fuel cells, which take natural gas, and instead of combusting the gas and air, it's oxidized over a fuel cell, and that allows us to generate electricity. Solid oxide electrolyzer cells, which take electricity to produce hydrogen, or then integrating a natural gas combined cycle plant with an electrolyzer, running the solid oxide fuel cell in reverse, or integrating the SOFC and so the solid oxide fuel cell and the electrolyzer together. So these are different concepts to produce either electricity or hydrogen. And these are rigorously modeled with really very nonlinear equations in the IDEAS platform. And each system has order of magnitude 5,000 equations. We're able to solve and optimize these problems, but 5,000 equations for every instance of the steady state model is a very high computational problem. So what we did is we wanted to deal with that. So we formulated our price taker optimization problem. This looks a little bit different because in addition to revenue from power, we also have revenue from hydrogen. Our inputs are the electricity price and the hydrogen price, and we have different operating modes. So some of these systems, either they are going to be off, they're going to be in power only mode, they're going to be in hydrogen only mode, or they're going to be both in hydrogen and power production mode. Now, I mentioned every concept that we had a very nonlinear model. And to get around the computational burden, what we did is we fit algebraic surrogate models, so low order polynomial models, or maybe polynomials with some logarithms or some division in them, to replace these equations here in our formulation. And then this allowed us to solve this mixed integer nonlinear program that we reformulated. We reformulated these disjunctions into a nonlinear mixed integer program. So now we have a way to take these energy prices and to optimize the operation and the design of the system, and it's very computationally efficient because of these surrogates. So we get results that look like this. This is just one system's results. I just want to paint a flavor of these results. So what's shown here is hours. So this is over about, I believe, a week or two. In red, we have the power output. And in blue, we have the energy price. And as expected, when the electricity price drops, we stop and we're not in power production mode. When the electricity price is high, the system's producing power at its full capacity. We're considering bimodal energy prices in this case. So this is a future forecast for energy prices in California with $100 per ton carbon tax. And in this scenario, our prices are bimodal. So we have most of our prices are really high, but occasionally we have really low prices. And this bimodal distribution is not surprising at all. We're even starting to see part of this in data from California, and it's really driven by renewables. So for a system that co-produces, we'll get results that look like this, where when the energy price is really high, you're in electricity production mode. When the electricity price is really low, you go into hydrogen production mode. So we took this optimization formulation, we got results that look just like this for all the case studies, and then this allowed us to do a systematic comparison. So shown here are the 6 case studies that I previously mentioned. They're ranked and they're evaluated under this pricing scheme. And there's a couple of really interesting things that we find. The first thing that we find is the solid oxide fuel cell technology really outcompetes natural gas combined cycle with carbon capture. This really is a very promising technology for producing electricity. Now, there's a lot of really great research that still needs to be done to bring the cost down for these systems, but under some modest assumptions for future costs, they do look very promising. What's kind of building off of that is hybridizing natural gas combined cycle with an electrolyzer doesn't make sense. It has negative profits per year. But if we, in this energy price signal that's bimodal, if we hybridize the solid oxide fuel cell with electrolyzer, or we run the solid oxide fuel cell in reverse, we actually get a really good system that outperforms these two standalone systems. So when you have these bimodal energy prices, you really do see an advantage to these integrated energy systems. And I really just want to emphasize this comparison is considering optimal operation of these energy systems over an entire year. And this optimization capability really allowed us to consider these time varying prices. So kind of coming back to the roadmap for this talk, we started talking about the price taker up here, where we have historical data and we use it as an input for an optimization problem. We started thinking about battery sizing and operation and degradation. We then spoke about uncertainty, and then we finally talked about comparing technologies and ranking them. So a couple of takeaway messages from this first part of the talk. So in our optimization formulation, we were assuming self-schedule. So what that assumed is the integrated energy system could set its production schedule, and we didn't consider the complexities of how the grid decides which power plant is on at what time. There's a little bit more nuance there regarding bidding and market clearing. Perfect information assumed it neglected forecasting error. And that's actually a pretty reasonable approximation based on the middle part of it, where we looked at dynamic load decomposition. And then finally, price taker assumed that our integrated energy system was really small, and it didn't have enough volume or capacity to sell electricity to really impact market clearing or the prices. So these are three really big assumptions, and using these these assumptions, we were able to set up this multi-period optimization problem that we could solve really quickly, and we could co-optimize design and operation, and we could actually get in a lot of insights. What I want to talk about in the second part of the talk, which won't be as long as the first part of the talk, is revisiting these three big assumptions and some of our recent work to come up with more rigorous ways so we don't have to make these assumptions. So before we kind of talk about the methods, I think it's really important to talk about models and the energy community in general. So I'm a chemical engineer, so I identify a lot with this left-hand part of the slide, where I think about building process models that have really detailed thermodynamics. Maybe we think about the dynamic operation and controls, and we do a really good job with the details of the process. But we treat the electric grid in this very cartoon note as an infinite bus that can always take the power that we want to produce, and we can take its prices. On the flip side are electrical engineers or power systems engineers. And they think about the subtleties in modeling the electric transmission system and how to design markets and how to clear and how to schedule kind of a whole region's worth of generators. So these are really detailed models that are focused on the transmission, and they treat these energy systems as kind of this really cartoon notion. Maybe they're really simple linear systems. And that neglects the process detail. And these communities and these tools are often applied in isolation. And these kind of cartoon representations work pretty well for traditional thermal generators, which you can model really well with these simplifications. And because the grid without renewables is fairly simple. This infinite bus approximation works really well. Where these approximations break down is in the electric grid of the future and today, where we have more and more renewables that have a lot more volatility and are causing a lot of changes to the market. So to break down this barrier and really capture the connections between these two paradigms, we came up with this so-called double loop workflow. And what this is a multi-scale simulation workflow that couples detailed models from processes and from the grid. So we're going to start here at the top of the day-ahead loop. We start by making some forecasts or having scenarios for future energy prices. Those are then used to solve a stochastic optimization problem to come up with these bid curves. These bid curves communicate for every integrated energy system how much power it's willing to produce as a function of market price. This is then used and collected for all the energy systems or all the power plants in a region, in a network. And then the market solves an optimization problem to minimize the overall system generation costs. We use Prescient, which is an open source production cost model. This happens in the day-ahead loop once per day. Now, these forecasts are inherently wrong. So we need to have recourse, and with that, there's a faster loop, the real-time market loop. So every hour or faster in the real-time market loop, the market resolves a dispatch problem to minimize system generation costs. That then provides dispatch tracking points to every integrated energy system that then needs to solve a tracking control problem that balances cost, health, and a tracking penalty. And then finally, that gets passed in to Prescient, which calculates where the money flows with the actual dispatch. So we've implemented this. This is available in Python using really detailed process models in Pyomo that are available through Ideas, and really detailed production cost models that are also in Pyomo available through Prescient. If you're interested, we have a recent publication on this. So we've taken this workflow, and we're going to contemplate how changing one generator changes the rest of the network. And we're going to do a little case study where we take this RTS GMLC, which is this representative power network, and we're going to take one generator in it, and we're going to perturb that generator. We're going to imagine we replace it with integrated energy systems with very different characteristics, and we're going to resimulate the electric grid operation over an entire year about 65,000 times. And this is going to give us a really rich data set that says how the energy market changes as we change the characteristic of one generator. And we can look at things like the frequency of dispatch. So here we can look at things like total revenue for this individual generator, and we can look at things like total time shut down for the generator. We then took all that output data and we fit market surrogates. So we fit surrogate models that predict as a function of the generator characteristics its revenue, and as a function of the generator characteristics its shutdown, and what modes of operation it was in. You know, was it at the minimum capacity? Was it at the maximum capacity? Was it at intervals in between? And we compared these with both algebraic surrogates fit with LMO, or neural network models fit with TensorFlow and Keras, which then get integrated into Pyomo using Omelette. Taking these surrogate models that map generator characteristics to market outcomes, we were then able to come up with a different integrated energy system optimization problem. So here we have an optimization problem where the market revenue is now a surrogate. We have the operating costs, but we have these surrogates that tell us how frequently we're going to be dispatched in every mode as a function of the generator characteristics. So we're able to take these surrogate models, these neural network surrogates, and embed them into our optimization problem to capture these market interactions. And this allows us to go beyond price taker. So we're able to solve this optimization problem. We can get some really interesting results. And I want to just show you one set of those results, which are on this slide. And what this slide does is it's comparing the price taker that I had at the beginning of the talk to this market surrogate. So just a lot going on here. Each circle corresponds to a different simulation where we're changing the marginal cost in the generator, so that we're doing a one variable sensitivity analysis. There's a couple of different profiles for each of these generators. Some are really fast startup, some are really slow startup. The solid lines are the surrogate models, so that are the surrogate models. Each dot we got from simulating the double loop, and the x's correspond with price taker. So what this plot allows us to do is understand when the price taker approximation is pretty valid and it makes really good approximations, and then cases where maybe the price taker breaks down. And this is a way that we're using these machine learning models to really bridge scales. So as part of this dispatches project, which is in a partnership with several national labs here in the United States, we're coming up with these capabilities to think about design optimization. We can think about formulating our design optimization problem either with price taker or with market interactions. And we can use steady state models or we can use multi-period models. That design optimization then gives us candidate integrated energy system designs that we can simulate rigorously with this double loop capability. That then provides new data that we can use to refine the market surrogates or the market data and repeat this loop. So this gives us another capability of coupling design optimization with actually simulating market outcomes. So finally, to conclude the talk, I want to come back to our roadmap. So what we've developed are optimization capabilities that allow us to really think about how to optimize integrated energy systems within a market. We talked about price taker first, which is really good to get a fast approximation, is really easy to work with, and is really becoming the standard in the community. We then talked about the limitations of price taker and some new capabilities that couple detailed process models and detailed market models to simulate these interactions and go beyond price taker. So some takeaways, the final takeaways from this talk: these integrated energy systems do in fact provide flexibility. And as we saw with the solid oxide fuel cells, co-producing hydrogen and electricity actually makes a lot of sense under bimodal energy prices. We're able to formulate these problems with optimization and co-design, design, operation, and control decisions. And then finally, we're able to take these multi-scale simulations and couple them with these machine learning surrogate models to go beyond price taker by directly incorporating market impacts into the optimization formulation. So if you're interested in the things that I talked about, my group has a lot of recent papers in this area. I have them kind of summarized here. And with that, I would be happy to take questions.
Alex, thank you for your interesting talk. So I appreciate the complexity of the problems the modeling the market. So congratulations, it's an awesome work.
Thank you.
So okay, we have a problem. Yeah. Okay. So well, we have some time for some questions. Start. Change. See. So we have time for some questions. You have any question, you can come here. See. Okay. So Alex, so we have a question about your data.
Mm-hmm.
How do you obtain this data for running your model?
Yeah, that's a great question. Okay, let me jump to a slide. Okay, so like the data that was used to make this plot is publicly available in the United States. So in the U.S., there's about approximately 10 markets. So different geographic regions that have that operate these wholesale markets, and they're required to release these historical prices. So there's a website that has an interface that you can download from. Some of them are more automated than others. So when I was a postdoctoral scholar at the University of Wisconsin-Madison, I was actually able to automate some of this and scrape a lot of this publicly accessible data that's necessary to make these plots. That's one way to get historical data. You can then ask the question of kind of jumping back to this conclusion slide. So historical data is here. What about production cost models? So those, there's some commercial platforms that you can purchase that have data necessary to simulate different regions of the energy market in the US. So that has information on all the different kind of available power plants and some typical demands. That can be used to create data. In this project, we used Prescient, which was an open source production cost model. So that's an open source market for the entire, like for simulating an electric grid in a wholesale market. And then part of Prescient, there's an open source data set that approximately looks like the Southwest United States. And that open data set's really nice for researchers, anywhere around the world to be able to use. There's no restrictions on using that data. So those are the two places where we can get the data, either historical data that's publicly accessible, or we can run a production cost model, either an open source or a commercial tool.
Okay. Thank you, Alex. So, any other question?
¿Te lo paso en español?
Sí.
El modelo considera el crecimiento de la población o solo la situación actual de los datos o cómo está su modelado.
Okay, we have other question, Alex. So, your modeling is used for the current state of the grid in California, or you have any perspective included for the future, thinking probably in demographic growing or market expansion, for example?
Yeah. So included in the IDEAS project, which a lot of this work was funded from, and it's highlighted here. There are also some modeling efforts to solve expansion planning models. So that what those models do is they look out into the future, 10, 20, 30, 40, 50 years. They make a bunch of assumptions about like growing demand for electricity that's maybe due to population growth or to people moving. And those models then ask what technologies would you install and how would you need to expand the grid. Inside the team, we've been thinking about where expansion planning models fit into this and adding another dimension to it. I just didn't have time to include any of that work in the talk.
So, I have any question, Alex, about the algorithm or Gaussian process that you included for solving the modeling. Can you explain explicitly how it works?
Yeah, so Gaussian processes in general, or
No, the specific application for solving your modeling.
great. Okay, yep. Let me pull up this slide. It'll be easier to do with the picture. Okay, so we have a conference paper from the American Control Conference that dives into the details. But what we did here is we had a Gaussian process model that used so many hours of training data. And then what the Gaussian process model's output would be the next time point. So a prediction about the next time point. And then we would use this model in a rolling horizon formulation. So we would make a prediction at this point, we'd shift the data set by 1, we would then make a prediction, and then we would kind of keep on doing that to build out this forecast. The other thing to note about a Gaussian process is what it's really saying is your prediction is normally distributed by a mean function and a covariance function. And that covariance function is what gives us these uncertainty bars. I believe these are plus or minus 2 standard deviations. But that's how we use the Gaussian process.
Okay, thank you, Alex. So nobody else have a question. So, well, Alex, thank you again for sharing with us your work. As I mentioned before, it is a waste of work due to the complexity. And well, here in Mexico, we don't have a liberalized market as California, for example. But well, for us, it's pretty important to take these things in consideration due to the future change that we have in transition and energy transition and energy markets in Mexico. So, thank you very much for sharing with us this interesting work again.
And thank you so much for the opportunity. It was my pleasure.
So clap for you. So that's it for this presentation. So thank you for everyone for attending. Well, have a good day, and well, I'll see you soon.
Yes. Thank you.
Okay.
Bye.
Okay.